Okay,
Yes.
cool.
And we should be live there now. So, don't tell any secrets that you don't want the internet to know about.
All right, so we're live. Okay, cool.
We are live. We are on the internet.
Nice. Okay, so Jonathan, thanks for inviting me.
Yeah,
Live?
absolutely. Yep. So here, we're still in the pre-show. Here in a minute, what I'll do is I'll go to just me and I'll do a brief intro, and then we'll actually start the show, and then I do a multi-track recording of this, and so I will edit it today, and it'll go out tomorrow as a Hackaday article. This live stream will be available till then, but tomorrow it'll go out as an edited podcast and article.
So I'm using this title. Live now on FLOSS Weekly with Jonathan Bennett.
Yep.
Talking about VectorCamp and SIMD.
Absolutely.
Do you use something different to promote, or some hashtag or something?
The only hashtag we would use is like hashtag FLOSS Weekly.
Hashtag FLOSS Weekly. Okay,
Yeah.
cool. Post it.
Very cool.
All right. Okay, let me know when you want to start.
Yep. Here in just a second.
Sure.
Just a tiny bit to do on my side. My wife earlier today was asking about who I was talking to, and she started to try to pronounce your name. Got, Constantin, and then stopped. And I looked at her and went, Constantinople? She goes, that's what I was trying not to say.
It is the same. Well, it comes from that. It's the name is Konstantinos in Greek, but it's actually a Latin name. So it's the name of that Roman emperor, which was named, became a saint afterwards, and then people started giving away names to their children after
Yes.
that saint and emperor. So it's Constantine in Latin, in English, but Konstantinos in Greek.
Constantinos.
Yes.
All right. I will try to not slaughter that during the show.
It's not that difficult, but
It's
okay.
it's really not.
Yeah.
And then your last name is Margaritos?
Margaritis.
Margaritis. Okay.
Yes.
All right. I think we can go ahead and get started. Make sure. Yep. It all looks good. All right.
Okay.
I am recording. Links are good. I think we're ready. Here we go. Hey folks, it's time for FLOSS Weekly. That's the show about free, Libre, and open source software. We talk about hardware, we talk about the personalities of open source, and today is going to be another great show. Today we're talking with Konstantinos Margariti about, well, a lot of things. His Debian background, SIMD and CPU architecture, the Linux kernel, a whole lot of stuff. It's going to be a lot of fun. I am flying solo today without a co-host. That is probably because of the holidays, but we'll make sure and get somebody in the co-host chair coming up again in the next few episodes. But anyway, without further ado, let me go ahead and bring on the guest. Hello, sir, and so glad to have you here today.
Hi, Jonathan. Thanks for inviting me. It's an honor. It's a pleasure.
Yeah, it's been fun already talking in the pre-show about things. And you started telling me a story about when you very first started running Linux and how it ties into being a Debian developer. And I said, no. Save that for the show. Well, we're now on the show, so let's dive into that. What did that background look like?
Okay. Right. So like many people, I tried myself with working on many computers back in the 90s, PCs and Mac OSs and Mac OS. And I got myself a Power Mac. Actually, it
Hmm.
was a Umax Super Mac C500 for those that are aware. It was one of the Mac clones at the time. And Mac OS was fine. It was great to use, but I wanted something more. I wanted more control because I had played with NetBSD on another computer.
Hmm.
I like the power that Unix gives you, Unix like operating system.
Yeah.
So I said, okay, let's try Linux on that. And it worked, sort of worked, but not really. I mean, there were many things that were really broken, didn't work. The graphics drivers, the software was buggy, and I started, getting into the code more, starting playing with it, fixing bugs,
Hmm.
and sending patches to the distributions. At the time, I ended up using Debian, and after a couple of years of bug fixing and sending patches, and using that as my daily driver, and some of the guys in Debian said, okay, hey, you're already doing half the job. Why not just apply to become a Debian developer? That was 99. I think it was March 99,
Hmm.
something like that. I don't remember.
Yeah.
And I applied, passed some tests, some interviews with, I don't remember the name, a guy in Germany.
Hmm.
And they say, yeah, you sounds good. You're okay. You're fine with us. And I became the first Debian developer in Greece. And
Very cool.
that that was an eye opener. It opened a whole new horizon on open source software
Hmm.
globally. I started interacting and talking with multiple hundreds of people all around the world, and everyone was different, but we all had one shared goal of promoting open source
Hmm.
and free software. It's not just open source; it was free software and open source software.
Yeah. Yeah, for sure.
So that evolved, and I became more involved into deeper places in the Linux system. I was really into, you know, I didn't care about front end that much. I cared more about the algorithms, optimization stuff,
Hmm.
and getting into the low level. Not too low, so I'm not a firmware guy or a Linux kernel guy, but I am more of the. I like optimizing algorithms. So that's
Mm.
how I became involved with a company that at the time was producing Power PC computers. That was Genesee USA. And through some other Debian developers, I got in contact with those people in the company, Bill Buck at the time,
Hmm.
and they liked my approach. So after a while of talking and I started giving away ideas and talking about how to optimize, use the SIMD unit in the CPU, G4 then. I said, okay, hey, why don't you work for us? And I said, okay, yeah, I would love that. So I started working on software optimization using the vector unit of the CPU, the CMD unit.
Hmm.
CMD meaning single instruction, multiple data. So for people that are aware, it's a small unit that provides extra instructions to the CPU that operate the same they provide the same operation on multiple data, multiple elements of the
Hmm.
same type. So it doesn't make your computer run faster, but it allows the computer to execute the same instruction on more data. So essentially giving you the idea that it runs faster.
Sure.
And it's used in pretty much everything.
Hmm.
So 3D, crypto, AI right now, AI is just math, right? It's just linear algebra, basically. Matrix multiplication, vectors, tensors, all this stuff. So anything that optimizes this kind of code, this kind of algorithm, uses one or more of those instructions in one way or another. And that always got me into, I like the idea of, okay, let's squeeze that much more performance out of your computer,
Oh yeah.
make it run faster. I mean, why just be satisfied with, I don't know, 1 gigahertz when you can make it feel like 4 gigahertz? That was at the time the idea.
Yeah.
Uh, anyway, so eventually that hobby became well, I wouldn't say passion, but yeah, sort of. And I started to become good at it, and I got more involved. I did some other work in the past, like I've done pretty much everything from Java Enterprise for front-end development, Linux administration, you name it. I mean, as I guess most of of that time. But yeah, the passion was always low-level algorithms and C and C++, but mainly around SIMD. Well, so I have to know, some people call it SIMD, some people call it CMD. So
Same thing.
yeah,
Yeah.
it's confusing
Yeah.
because the acronym means also something for medical devices. So it's
Not that one.
confusing.
Not that one.
Yeah,
We're not talking
not
about
that
that
one.
one.
No, we're not talking about that one. Anyway,
That's fun. Are you? Do you still
yeah,
do? Are you still an active Debian developer? Are you still in
yes,
Greece?
yes. I'm still in Greece.
Ah.
I did some time working for companies abroad, for Singapore, Cambridge, US, Germany, Belgium. So I've been around. But right now I'm working remotely. I started 5 years ago. I started my own company with my wife, and we now actually provide the services of what I was doing as a freelancer for many years. We're now doing it using our company. And ARM was our first customer, ARM themselves, which was a big surprise for us. So also a great honor, because having a tiny company in Greece, having the one of the biggest CPU companies in the world as the first customer, that's something.
Yeah.
And one of the first projects was to port Hyperscan. So Hyperscan, I don't know if you're aware, Hyperscan is an Intel project that is doing the massively parallelized regular expression matching. So that's a
Oh.
mouthful.
Yes.
Yeah, so it performs, let's say, regular expression matching on thousands of regular expressions, almost in real time. It's used in security appliances, intrusion detection systems, Snort, Suricata,
Yeah.
even genetic algorithms, genetic pattern matching. So it's a very versatile library. But the problem was that it runs only on Intel. And there were a couple of attempts with some ARM vendors that were trying to port it to ARM, but they could not get the performance they wanted. And I met this guy online, Robbie Williamson from ARM, and he said, okay, I know you're doing CMD stuff. Would you be interested in taking up this project? Say, okay, sure, of course. That's a huge honor and a great challenge for me. So, and we did, and we ported that project to ARM, and we sent the pull request to Intel. Intel, for their own internal political reasons, they did not want to accept the pull request, so they rejected it, and that gave us only one option basically. Well, the first is to constantly chase Intel and the project and apply all these patches on top. And the other was to fork the project,
Yeah.
create a new project, a new open source project, and stop chasing Intel and move forward in a different direction.
Right.
And that's how VectorScan was born. And initially it was just a couple of patches on top, but after a while it became a project on its own. And it became also the only successful Hyperscan replacement, because currently, unfortunately, Intel closed the project in late 23, I remember, and it's now proprietary. So you can get the last open source version, but there is no development anymore. Intel does not really, maybe they are doing internal development, maybe they are providing customers, their own customers with extra versions, but it's not open. So users cannot base that, cannot get those extra versions that they are being produced by Intel. So that really gave us, that was a big opportunity for us, to be honest. because we became the only alternative for open source projects. And right now, except for Intel, we port it. We get better performance on Intel for one thing. We get 10% better performance on the same Intel hardware. We have ported to ARM. We got patches from ARM themselves for SVE2, so that you can get even more performance on SVE2 enabled hardware. We ported to Power 9 from IBM, which was not possible before. And we also ported to the CMD Everywhere library. It's a C library that provides a platform to run on every architecture that lacks CMD support for a particular for some instructions. And this has the nice added bonus that you can compile and run the library on software on CPU architecture that lack any support for CMD instructions at all, not just incomplete support. But let's say you're a vendor, you create a new architecture, a new CPU, and you need some library like that, and you don't have a CMD support already, but you want to test if your front-end software, if your appliance is actually going to work. And CMD Everywhere provides this kind of emulation, and you can run it. It's going to be slower, but it's going to work. And our next step is to provide more support better support for newer instructions in Intel, ARM, but also RISC-V is very important. It's becoming much more important in the free software world. It's not very fast right now, but it's going to become better. Actually, I have here.
I just so happen to have.
Yeah, you know this. You probably know this. This is one of the deep computing RISC-V boards. And I'm about to set it up to become one of the first builders for this kind of thing.
That's cool.
So it's not a speed demon, but it will get the job done.
Yeah.
Of course, I have lots of ARM hardware like ARM servers and Ampere systems and some SV hardware. My wife says that I have too much hardware.
Nonsense. It's not true.
Yeah, it's not enough. It's never enough. I still like a mainframe, but okay, maybe. Anyway, so
my wife is watching the show right now, and she is getting quite a kick out of this. I just so happen to have. Yes.
Yeah,
yes.
it's really. I mean, I'm also a collector of retro hardware. Behind me, I have just a small collection, some Amiga, Spectrum, and some other stuff. But this is just 1/10. I have about more than 100 retro computers in another place. It's I don't have them right now available, but
I get it.
Yeah, it's
100%.
It's like there you can never have enough retro computers.
Exactly.
Exactly.
I've not been bitten by the retro computer collection bug, but I do have my own share of hardware and so many things that are within arm's reach that I could say I just happen to have. Mine these days tends to be a lot of ESP32 stuff, ESP32 and like Nordic and STM.
I played with that in the past. It's a thing. So it's at some point you have to, I wouldn't say decide, but some of the stuff you have to decide if you want to run them, if you want to focus on high-end servers or low-end devices.
Right.
Most of the algorithms are, I guess, the same, but there are some things that you just cannot do on low-end devices.
Yeah.
But I absolutely love the amount of optimization that goes on into the low-end devices.
Yeah.
Because you have to squeeze out the last bit of performance, and that's amazing. I have enormous respect for the developers that are constrained, like the developers in the 80s. You were constrained. You had 16 kilobytes of RAM to play with.
So
and you have to do wonders with that.
In another example of it, I just happen to have, I've got the Hackaday badge from the conferences.
Yeah, I've seen that. It's really cool.
It is. It's a very neat piece of hardware. So a couple things about this. It's a ESP32 S3, I think. And I said, hey, send me a couple of those and I'll put Meshtastic on them because that's the project that I spend a lot of my time on these days. I made the port work. I got it running. And like a few hours after I did that, I felt really good about myself. A few hours after I did that, somebody's like, oh, by the way, I got the Linux kernel to boot on that thing. Like, well,
Cool.
okay. Yeah, exactly. I thought it was big stuff until he told me that.
There's my weekend again.
Exactly. It's interesting.
I know how that feels.
It's interesting though that you can run. It fascinates me to no end that you can run the Linux kernel, all the way from the big iron mainframe machines, all the way down to a microcontroller. I didn't realize. I did not know this was possible.
It's amazing.
Are there SIMD instructions on the microcontrollers, or is that just sort of outside of their realm?
Yes and no. I mean, ARM have their Helium. Well, there are some minimal set of SIMD-like instructions that work on the ARM embedded devices. It's called it has a weird name. I forget about it. They are not exactly SIMD, but they follow that label, that philosophy, to run the same operation on multiple elements in the vector, in the register. However, ARM just recently announced a few embedded CPUs that provide the Helium extension, which is very similar to Neon or Advanced CMD, but Neon is the low end, the 32-bit variant.
Right.
Everyone calls it Neon, even for 64-bit, but ARM technically will tell you, it's not exactly the same, but more or less the instructions are following the same pattern. There are differences, of course. Anyway, so the Helium variant is very, very similar to Neon. So if you have programmed Neon, you will find it very easy to migrate your code, with some exceptions, of course, because not everything is available. And by the way, if you are interested in getting, programming in Neon, I just got last week this book. Sorry.
Oh.
And by the way, this goes together with this book. So this is not an advert. I'm not doing marketing here, but I saw a video from Matt Gobold, from Compiler Explorer, and he interviewed the writer Daniel Kuswer, and he said that he was presenting his books, and I said, okay, these are really must-have books. I ordered them immediately, and I'm reading them right now. They are really very good books, and they are what is missing from developers right now, because you can find documentation and reference, and some, let's say, books on really outdated standards for Intel processors, but there was no modern book for CMD development. And I bought those because I want to fill in the gaps in my knowledge. I mean, I've been doing 22 years of CMD, and there is still things that I don't know. I've never worked on, or I'm still reading, oh yeah, there's that, look at that register, I didn't know about that. Stuff like that. So you keep learning, and I keep reading about this. Yeah. And having this book, sorry.
I was going to go in a different direction, but if you wanted to say something else about the book, go ahead, and then I've got to follow.
No. I mean, it was good that I was able to find that there is someone wrote some books about this, because I wanted to write a book about CMD for many years. I started an effort to write a comparative reference, but it didn't go well. I wanted to list every single instruction for every operation in every architecture. And I had written about 100 pages, and I was still not done with addition. So I said, okay, this can never go into a book. This is never going to into a book. And say, okay, I'm going to turn that into in an online resource. And the idea was to create some kind, way before AI was popular. So I talked with an AI professor in 21, I said, okay, look, we want to do this. We want to create an AI that's going to translate code from one architecture to the other.
Oh.
Isaac Cavasidi, he's a professor in a University of Catania in Italy, and he's a friend of mine. And he said, yeah, that's a great project. Let's scan a few projects in GitHub and see if we can gather enough data to get this running. There were some promising results, but his constant complaint was, we don't have enough data. There is not enough data. So, okay, point taken, we only have one solution. We are going to create the data ourselves. And this is what led to the creation of cmd.info. So if you go into that website, after 4 years of very painful manually classification of pretty much every CMD intrinsic out there for the three major architectures, Intel, ARM, and Power. We have like 10,000 intrinsics there categorized in a it's not just a generic, okay, what's wrong with Intel intrinsics guide or the ARM intrinsics guide? They're fine, but every vendor is going to provide all the information for their own architecture only. So if you let's say you're an application or a library engineer or a kernel developer, you want to see, okay, I want to port this code from, let's say, x86 to ARM, or I have this power from an old legacy power system and I want to port it to ARM. Yeah, I have to look up on the documentation, and finding all the documentation in 3 different places, and sometimes not even in a proper online resource. You have to go and read thousands and thousands of pages of reference manuals for architectures, and different variations of those. Yeah, you're wasting. There goes your week. Okay, especially if the code is complicated and there is no, as in many cases, there is no one-to-one mapping. If you take away the trivial operations like addition, multiplication, load, store, this kind of stuff, all the other instructions, they basically don't map to each other one-to-one. They're different, slightly different at best, or completely irrelevant from one architecture to the other. And so I said, okay, we need to have an online resource. We did a very fine-grained categorization, extremely detailed. So every operation you're going to find, this is very detailed down to the element level. And why is it needed at such detail? Because the idea is that we're going to use that as data in an AI. LLM is one variant. We tried that. It doesn't seem to be working, but an AI nevertheless. Why? Because you're training it. You're giving all the data.
Yeah.
And you can ask it afterwards, okay, I need to translate this code from one architecture to the other. It's going to go back. It knows the operation. It knows the details about stuff like, okay, how do you translate this? What's the operation equivalent between those 2 instructions for these 2 architectures? And it's going to give you, okay, this exists, but this one doesn't have a mapping. And the AI is going to go back one step further and say, okay, there's no equivalent. What can I do with that? I know the operation, so I'm going to try to reconstruct the operation with what's available. This needs a lot of work. I'm still working on that with my team. It's promising. We wrote some blogs on the same platform, cmd.info, and we chose a 24 billion model to fine-tune with our own data. And we actually provided, we created an open source model, an open source project to compare all these results by sending them to ChatGPT, Claude, DeepSeek, DeepCoder, and some other models. We actually evaluated about 40 models in total.
Oh, wow.
And we managed to beat every one of those for trivial cases. And for some not so trivial. The problem is that when you give it something more complicated, every AI is going to collapse.
Yeah.
So
Yep. For
that's
sure.
what I keep saying to people. I mean, yeah, AI is going to help you write code. It's going to be very, you know, how to say, if you handhold it, if you
Yeah.
really give it a lot of instructions and guide it through all the process, what you want to do exactly and how you want to achieve it, but you really must know what you're talking about. I mean, you cannot just say, okay, take this code, this 1,000 line CMD code, translate it from one architecture to the other. No, this is not going to work. Forget it.
Indeed. I've
Yeah.
people that make good use of AI have made the point that it basically works like a very junior developer, and it needs a
And no,
senior
no,
developer.
even worse, even worse. I know junior developers that are really very good at translate code between architectures.
Sure.
It will take them slightly longer, but they will do it.
Yeah. Yeah. The point being though that it acts like it lacks a lot of experience, and it needs someone that's experienced to hold its hand to get the results that you want.
Yeah, exactly.
So you mentioned just now C code, and this is a question I was going to ask. Are we talking about when we're doing SIMD work? Is it a lot of is it C code, or are we writing at lower levels than that? Are we doing actual machine code?
Okay, good question. So, of course, the best performance is you're going to get with assembly, right?
Yeah.
So there's no discussion about that.
Well,
You always have complete control of that. Of the hardware.
If you're a skilled assembly programmer,
Yes,
my assembly
correct.
code would not do very well.
I've done a lot of assembly, but I will not go to assembly unless I really have to.
Sure.
Unless I'm, so you can get 80% of the work. It's like the 80-20. You can get 80% of the job, of the performance you want, using C and C in intrinsic,
Yeah.
right? Which is essentially a wrapper on top of assembly instructions
Yeah.
most of the time. The problem is that if you really want to squeeze the hardware as much as possible, there are some things that you really cannot do that easily with C and CMD intrinsic. You have to revert to assembly. And that's where I'm at. I really at the point where it's not enough for me. I mean, C code, it's a very good first attempt, but if I want to get the max, I'm going to revert to assembly. And assembly is going to give me the top performance it can give me. I'll give you an example. So RISC-V has recently released their own CMD, well, vector. It's not exactly CMD, it's vector extensions. It has some CMD ideas, but it's more closer related to the Cray vector instruction from 1970s, because they are following the idea that the vector is not a fixed length. It's more like, I set the length of the vector, and I decide on the operator and tell you, okay, start, iterate, do this algorithm on top of every vector element, and then when it's done, that's it. I mean, compared to traditional, let's say, SIMD, you have 128 bits, which is 16 bytes, or 32 bytes, or 64 bytes with AVX512.
Fixed widths, yeah.
SVE is in the middle. It can give you up to 2048 bits. SVE2 from ARM, but it's more implementations are more limited, like 128 bits, 256. To my knowledge, there is no 512 yet. RISC-V is a bit more open in that aspect, so you don't have to change the code. You don't have to recompile the code. You don't have to rebuild it for every variant in the vector. With SV2, that's one big drawback. If I have let's say a CPU that provides 128 bits, I compile my SV2 code for that architecture, for that variant. I can run it on the 256 variant, 256-bit variant, but not the other way around. If I compile my code to run on the 256 variant, it will not run. It will not run.
Yeah.
On the it needs a recompile. I mean,
and if you compile it for the if you compile it for the 128, it'll run on the 256, but it'll run
Yes.
slower than it would if you recompiled it for that particular
I know.
architecture.
Okay, someone is going to say, "Yeah, liar. This is not incorrect. This is incorrect." So, okay, here's the thing: if you do a runtime detection of the vector size, yes, it will run because it will detect that the vector size in both cases, in one case 128, and the other case 256 or 512 or whatever, and then it will run the algorithm correctly. But if your, let's say, code depends on the vector size being fixed, like if you have a fixed algorithm for DCT, for example, discrete consigned transformation, and you wrote your algorithm for 128 bits, and you depend on your size to be that long, then it will probably run on 256. But if you depend on the vector size being 256, then you cannot make it run on 128. Well, it will run, but it will produce incorrect results. So it's a bit of a problem right now with ARM. My guess is that it will mature and people will provide the better solutions in the next years. RISC-V is a different kind of problem. There is quite a huge variety in the ecosystem. Too many vendors, too many CPU variants. There are CPUs that provide the RVV 1.1. There are others who don't. And that's why they had to create the RVA23 standard, which sets a baseline. Okay, so if you want to be called baseline architecture for RISC-V, you have to provide and support these extensions. And RVV 1.1 is one of them. I hope it will work out because before that it was very, very difficult. And you would have compile code that was depending on this extension, but the other vendor would not include that extension, and your code would not run, or it would segfault, or it would give an illegal instruction, like kernel exception, stuff like that. So they were in the same place that ARM was 20 years ago, and thankfully they fixed that.
It's kind of the downside, if there is one, to having a completely open source ISA the way that RISC-V is. It sort of turns some of that into the Wild West, and you get that fragmentation problem.
Exactly, yes. And now the problem with RISC-V, which is going to be also a problem for us, for CMD, the goal is to integrate it into CMD.info, right? And you check the statistics on the side of if you go to intrinsics tree, you see the statistics, you see about 10,000 intrinsics categorized, right, classified, all right, put it into the knowledge base. So 10,000 is a big number. We're going to add the long soon, LSX and LASX, which is another, let's say, 1,000. And some MIPS, obscure CMD architecture intrinsic, which are very small. We recently added the mainframe Z, which was a very small number, like 167 intrinsics. Now the fun starts with RISC-V. RISC-V on its own has more than 20,000 intrinsics.
Oh my goodness.
Yes. You see the problem.
Wow.
Well, yeah, and that's a problem. And to be honest, it's a lot of work for us. And this is not a project that is going to be... this has not been funded by any company, by the way. This is just because we had a passion for CMD development. We have done multiple CMD optimizations for pretty much every architecture there is. And we wanted to find a way to help other developers. So providing the CMD.info knowledge base was the first step. CMDI was another step. That's still, it's not gone as an idea, but we've put it on hold because we need to think how it's going to work, because just an LLM is not going to work.
Right.
But we also created a VS Code plugin that integrates all this information into your VS Code environment, your IDE. So if you go into let's say a CMD code with CMD36, and you hover over an intrinsic, is going to list all of the details of the instructions, the latency information for every CPU model that supports this instruction. Like this instruction, let's say Ampere is going to cost two cycles latency. On Cortex, say 553, for example, is going to cost 5 cycles or something like that. So someone that is going to be working on high performance code and performance critical code, they really want to look at that information.
Yeah.
Now, we really would like to include pretty much every architecture there, and I have to say that I did contact every company, and they were all, yeah, it's nice, but yeah, we're not going to fund this.
We're not going to pay you for it. Yeah.
Yeah. With ARM and IBM, it was simple. With RISC-V, it's a bit more complicated. The foundation is interested. I mean, to a person from that I thought they would like that, but they don't have the budget for that.
Right.
And but the problem is with the RISC-V vendors. I mean, they would all like that, but because they are essentially competitors to each other,
Yeah.
they don't want to add a competitive advantage and pay for themselves only. Anyway, so if someone from that side listens, we will be happy to take up on the task and include that information in the documentation.
Yeah.
And to be honest, I would be happy to open source everything in there. I mean, it's open, but it's not open source yet.
Got it. It's really a challenge for RISC-V, isn't it? I've seen some of the distros have complained about this too, because there's not the various implementations of it are so different. There's not an easy way to do, and I guess we have the same problem in some cases on x86-64. Like Intel and AMD can't figure out whether they want to make AVX 512 standard everywhere or not.
Oh yeah, please. That's a whole different game. I mean, it's AVX 512 is like it came out in 2013, right?
Right.
And until a few years ago, people were still considering, maybe. Well, Intel was considering maybe we will drop it from next revisions of the CPU. And what do you mean? Everyone is considering this to be a standard right now. You extend things. You don't just drop a complete architecture.
Yeah.
Or sub-architecture standard from your CPU.
I mean, the Linux kernel guys, they consider that so important that's x86-64 v4. That is one of the main differentiators.
Exactly.
It kind of blew my mind. I looked into that at one point, what people were actually doing with it, and the fact that you can use it for string comparisons.
Yeah.
Which is actually really pretty similar to your regex project.
It uses, yes.
That really it really fascinated me that you could use, maybe one could say abuse those 512-bit wide instructions to do string comparisons.
That's the idea. That's the idea. Cool. And so there is one problem in. AVX 512 is a huge monster. It's a very powerful monster, but it is one that takes a lot of space on the CPU, on the die, and I understand the CPU architects maybe we can optimize this away, or maybe not include it in the CPUs that don't actually need it. But it's a risk. I mean, you gain a lot. The problem is that not every software uses it. It's 12 years later, and not every software uses it.
It's kind of a chicken and egg problem, isn't it?
Yeah.
Not every software uses it because not every processor supports it.
Yeah, that was... I could understand that being the case 5 years ago or even 10 years ago because it was a new CPU. But right now, it's pretty much in every CPU you buy out there. So in every Intel and AMD CPU.
Didn't Intel
except
drop...
the really low end.
Yeah, I was going to say, didn't Intel drop AVX 512 out of a bunch of their new CPUs? Yeah,
correct.
Thanks Intel.
Exactly. So they just shot themselves in the foot. Well, I understand that they want to get the energy efficiency features of the newer CPUs and only include what's really needed, like AVX up to AVX2, which is also a very good extension. But AVX 512, well, they should, I don't know. I don't know what is the proper solution. Ditch everything and start from scratch. Keep adding stuff on top.
Yeah.
I mean, ARM has a benefit there because they have a much better, more orthogonal architecture. They still have added many instructions. I mean, if you look at the number of instructions that ARM has piled up on top of the architecture, that's comparable to Intel.
Yeah.
If you also include SV2 and SVE, and still they get much better battery performance and performance in general. So if I did many benchmarks, and the numbers that I could get, for example, by the Apple CPU, the M1 up to M4,
Mm-hmm.
I didn't try the M5 yet. They are mind blowing. I mean, they completely destroy everything. I mean,
Yeah. They're
short
really.
of a Threadripper and a very high end model at that,
Yeah.
the M4 is currently the fastest thing you can buy. Well,
Mm.
M5.
Yeah.
But then again, it doesn't run. I have a MacBook, but I gave it away. I'm sorry to say that. Because I need Linux, and I was using everything in a Linux VM inside the Mac, and I was complaining all the time to ARM and to, hey guys and Qualcomm, please get your stuff to bed. Get a Linux laptop that works on ARM architecture. It's going to sell a lot.
Yeah.
People are really going to buy this.
I have for a while now been tempted by the idea of buying a couple of generations back Apple books. So, maybe an M2
Yeah,
or an M3 and then running Asahi Linux on it.
yeah.
Uh,
I have one M2 here. I'm going to play with Asahi at one point.
yeah.
So
I know some people have had very good experiences with that. We were talking about the x86 world, and one of the things that is being talked about right now is dropping 32-bit support out of x86. I'm curious if you have any thoughts on that.
uh, well, it's a risk. I understand the point that okay, 64-bit, it's like it has been around for 20 years almost.
Mm-hmm.
It's pretty much a de facto. I mean, every system you're going to buy is probably going to be 99.98% is going to be a 64-bit. But if you miss that, if you drop 32-bit in general, that means you also drop support for embedded. So there are many embedded
Mm.
CPUs that are still produced and sold by every vendor
Mm.
that produce. I mean, ARM, RISC-V, some microcontrollers. They're 32-bit. So apart from the kernel, some of those operating systems there use third-party and open source libraries. If you just drop 32-bit support everywhere,
Mm.
then you risk the possibility, okay, that my software is not going to be running, it's not going to be able to run at all on microcontrollers. Of course, that's a problem we're not going to have today. But in 5 years, if this does happen,
Mm.
and if I see discussions in every architecture, in every distribution, Debian is considering dropping 32-bit. So actually, 32-bit is all actually it's gone. I think
Yeah.
ARMHF, ARML is dropped. ARMHF is going to be considered for next version,
Mm-hmm.
for the next release. By the way, RMHF, I didn't mention that. RMHF was, I could say, was a child of mine.
Oh.
In 2000, in 2009, I was working for this US company I told you,
Mm-hmm.
Genesee, and I was on loan to Linaro.
Okay.
Linaro is the consortium pharma companies at that time, and there was this discussion at the time too. Okay, ARM was using the soft float ABI, and there was discussion of converting to and migrating to the hard float ABI,
Yeah.
which would increase performance for floating point applications. And everyone was like, yeah, we don't know how much it's going to increase, and we don't know, and it's too much work. We have to recompile everything, and it's going to take years, and it's a lot of work. So, okay, I'll do it. And I used a bunch of Ethica MX smart tops, computers with running at 800 megahertz and 500 megabytes of RAM. I had a cluster of those, and I basically rebuilt everything by hand, manually, long before the bootstrapping operation was more streamlined and automated like it is right now.
Mm-hmm.
and that was used to bootstrap the official ARM-HF board in Debian. So everyone took it from there, everyone else. Now
Yeah.
the thing is that ARM-HF did indeed prove to be much faster than the than the soft float ABI. There was this benchmark that I was showing to an event. Actually, we went in, where was it? San Antonio. I was in the US at the time, San Antonio, Texas. There was an FTF, Free Scale Technology Forum, something, in 2005, I think. No, sorry, that was in 2010. And we demoed that. We had two systems running RML and the soft float and hard float. And the hard float was running 3 times faster than the soft float. So on the same CPU, same software, recompiled in a different way, that was 3 times faster. So that was a thing.
I remember the ARM-HF being really sort of coming into its own with the release of the first Raspberry Pi. That was the
Exactly.
first. I think that was the first piece of ARM hardware that a lot of us got a hold of that had that hard float in it.
Yeah.
And,
well, there were other CPUs as well, like the NVIDIA Tegra 2, I think.
Yeah.
The smart tops and smart books from Genesee, the Efficace, which were really cute devices, really nice. I find it a pity that they didn't get more popular, didn't get a newer version, but they were really nice. Like 10-inch smart book, a laptop that could take like 10 hours of battery time back in 2010, right? That was amazing. And but yeah, it is what it is.
Yeah. I remember having to sort through various Linux distros to try to find the ones that were actually compiled for ARM-HF. And some of the fun of that time period. We have it so nice today when everything is just ARM64 and it works everywhere.
Yeah, that was not the case back then.
No,
I mean,
no, definitely not.
you had to really pray that, or really spend many weekends to get the kernel run on your hardware, especially if it's a completely new.
Yes.
Yeah.
Yeah. So
that was terrible.
Yeah, it was trying times.
Yeah.
You mentioned a really interesting target, and that's the Longsoon. Here at least in the United States, we don't get to play with these at all. But I'm curious, what's going on with that? What are you seeing with Longsoon? Is that something that other people outside of China are looking to pick up?
I'm not looking to. It's very difficult to get hold of.
Right.
I bought one. Actually, I bought 2. I bought one version. I have one of them, but it's really under a pile of boxes right now. I managed to brick that with, so that's, I have to fix this. It's funny. So I had to make this work, and it apparently needed a firmware update, a UEFI update, and I feel very stupid by saying that. So I downloaded from GitHub the UEFI update. I flashed it onto the on the UEFI, and then it didn't boot. It was bricked. It made just a noise, a beep.
Beep.
And I say, okay, what's wrong? What went wrong? What did I do wrong? And it occurred to me that I flashed not the raw file from GitHub, but the actual HTML page. So, and apparently there were no safe.
There's not an HTML
measures.
converter. Yeah.
Yeah, or something like that to check for the file. I mean, the command to flash just took a binary and flashed it.
Yes, that's
onto
great.
the chip. So I have to reflash it using an EEPROM. And anyway, but at one point I did use that platform. I had to order it from China, spend about 200 euros, which is, I guess, about $230, something like that, on the customs import, on import duties. And that was really really difficult. I guess right now it's going to be even more difficult.
Yeah.
As an architecture, it's interesting. It's based on MIPS, but they have taken it to an entirely different level. So so their original Long-Sun architecture was really a MIPS system, a MIPS CPU. And it is the only system that I could find available that has the MIPS CMD architecture, the extra CMD unit in the CPU. I could not find any other CPU that I could buy. And even that, I had to contact the Long-Sun company and say, okay, I'm looking for this board, which is an old version. Do you sell it? It's not available anymore. Yeah, okay, but do you have something? Okay, we can sell it to you for this. I don't remember how much. It was not very expensive, but
Yeah.
still, it was. I had to contact them directly, and they had to create an extra entry in the Alibaba or AliExpress for me to go and purchase it.
Somebody
Anyway,
had to
so,
walk down to the booth there in Shenzhen to pick it up for you.
yeah, something like that. I don't know. They had to find it in some inventory forgotten, and interestingly, the board works, but it's very buggy, so it's not usable. It freezes every while, and every 10 minutes it freezes, and so you cannot do really any work on that.
Huh.
And my only interest in that was for the CMD unit.
Yeah.
The next version was their new CPU variant, the Long-Sun architecture, so Long Arch 64.
Right.
And that includes two CMD variants, the LSX, which is 128-bit, and the LASX, which is the 256-bit variant. So luckily, and I guess they did it on purpose, they modeled all the CMD intrinsics from the Intel instructions. So they have a one-to-one almost
Oh,
mapping
nice.
from these instructions to their own, from the Intel instructions to their own, which is, I guess, good for them because they don't want to spend a lot of time to port code from one architecture to the other.
It's clever. It's clever.
Again, there was a lot of instability in the system. It would still freeze, and I could not get the drivers working, and it did not see my network card, or it did not see the built-in GPU, or it was freezing after some, I don't know, 10 minutes of compiling, and it would just lock up. So it's not yet ready. Well, the model that I got, at least, it was not ready for production, but that was 2 years ago. My guess is right now is maybe the stability problems are fixed, but it's going to be extremely difficult for someone outside of China to buy it.
Yeah.
So it's an interesting take. I see that there is going to be, the world is not divided anymore just in geopolitical borders. I mean, technology is also getting separated. That's why this is not my idea or my philosophy. Someone explained that to me. So the technology world seems to be divided. So China has their own architecture, Long Arch, and also they are investing very much on RISC-V. Intel and ARM are very dominant in the US and Europe.
Yep.
Africa seems to be an open ground for everyone, but ARM is also extremely strong in the African region, and because I'm also a distinguished ARM ambassador, which means that I'm very vocal about promoting the ARM architecture. I am, but the reason is because I like the from the technical point of view. It's a very clean architecture. It's very good. I also like the power architecture. It's also very clean and although it's a bit old by today's standards.
Yeah.
And I'm also in the power architecture, the ISA, the working group for evolving the power architecture. My company VectorCamp is a silver member of the Open Power Foundation. So we're interested in all the architecture, basically.
Yeah.
So we want to promote all the architectures. And we're looking at it from a technical point of view, and we want to, okay, let's say you have software that runs in that architecture and you want to port it, or you want to make it even faster for Intel or ARM or whatever. We do this kind of service. This is what we do. We provide optimization services, basically. Yeah. So anyway, closing the parentheses.
Do you see a future for the power architecture? They're working on another ISA. Is that going to have a resurgence, you think?
Well, they obviously have. I mean, Power 11 just released, but and I know that some people from IBM are going to say, "Yeah, you're preaching to the choir." I mean, we know that we're trying to solve it, but if something doesn't change from the management level, then the architecture is probably going to die in, let's say, 5 years. Well, the problem is that in order to maintain an architecture, you have to maintain a developer base.
Hmm.
Currently, I don't know of anyone except some really uh, people, some developers that are really passionate about the architecture and also passionate about the openness of the architecture, because Power is one of the more open. I mean,
Hmm.
RISC-V is also very open, but Power was there first, and there is also a completely free platform like the Talos 2 workstation
Hmm.
from Raptor in the US, and it's probably one of the most open, if not the most open architecture system that you can buy right now, and it's based on Power 9 architecture. I have one myself,
Oh, very cool.
and it's really great. Even by today's standards, it's not fast by today's standards in the CPUs, but it's really good. So you have like two 22 core CPUs by with 4 threads each, like 192 or 196. Anyway, a lot of cores,
Yeah.
right?
Power 11, that is basically limited to IBM mainframes at this point, isn't it?
Yes, and that's my constant complaint to IBM. Constant. I mean, there has not been a meeting or a time that I don't complain to them and to OPF and to IBM guys. Guys, you really need to get a developer system out there. I mean, it doesn't have to be a Raspberry Pi, like costing $100, but you have to get something that is Threadripper or like the equivalent of Horizon system, costing 1,000 or 2,000 or even 3,000, something
Just
like that.
just less than $100,000 to be able to get
Yes,
started with
exactly.
one
I
of
mean,
these. Yeah, absolutely.
even for me, I'm a developer. I'm using that, and I cannot buy this because the minimum system you can buy is 50k, 50k.
Yeah, yeah, it's crazy.
And I say, okay, how much? I said, okay, I know people. If you don't want to do it yourself, I know people who can do it. Let us build it.
Hmm.
I mean, I know a company that can do it, and I'm sure there are many more, even more competent companies that can do it. But just allow them to do it. Give them the chips and let them build the CPU. The board. I mean, the only thing is the board. I mean, if you can build, let's say, a very small. I offered. How can I say it? If you could get, let's say that you are an open source, a free software advocate, you could get an completely open platform
Hmm.
for, let's say, a fixed memory amount, like 128 gigs, which is like the DGX Spark, right?
Right,
It's not
right.
bad.
Yeah.
And you could get it with a PCI slot, networking, basic VGA, and or HDMI, whatever. And you could get such a system for 3K, similar price, but it was a completely open. It had a very a Power 10 or Power 11 chip
Yeah.
in a small form factor, like micro ATX, if possible mini ITX, but I don't care about that. I mean, it's small, normal PC-like form factor. I know plenty of
Not
developers,
not a
but
huge
not the
rack. Yes.
mainframe, not a
Yes.
huge rack.
Uh,
And use off-the-shelf parts, like use the same heatsink standards, like someone can get a Noctua, for example,
hmm.
right? So I would buy that.
Yeah.
I know plenty of people who would as well.
Yeah. It's yeah. I've looked at some of IBM's offerings before and gone, oh wow, that would be really nice to have, but oh my
Oh yeah,
goodness, I can't. Yeah.
yeah.
All right.
They
So
are really good.
yeah. So looking forward, what do you see sort of on the horizon in the CPU, the open source, the CPU business in SIMD support for them? What should people be paying attention
Uh,
to?
okay, so that's not okay. So I have to be both a realist and an idealist. I know that the realist in me sees that more and more instructions are going to be put into the architectures and the CPUs, and this is going to be even make the situation even more complicated. Right now, you have thousands of instructions, and new developers are completely overwhelmed.
Hmm.
I mean, if you have to go to read a 1,000-page book to learn how to do something that is a bit more advanced, like okay, add this the elements in the matrix or multiply by a vector. Okay, this is a trivial case. But there are much more complicated cases like crypto. There are very specialized instructions for crypto, or video codecs, like the butterfly DCT instructions, which are completely a mess. And there are numerous variations of the same instruction over and over again. So one thing that I would wish is for someone to produce something simplified. So I would like myself, even though I'm working with this, I personally would like return to the basics. So okay, let's start with okay, what's the base we have here? Okay, we can take a RISC-V base core and add a new extension, not the RVV extension. Why is that? It's a perfectly fine extension, but it tries to compete with all the others, which are keep adding stuff on top.
Right.
My take would be different. I mean, my take is okay. I'm going to. This is a personal idea of mine that I would really like to work on. Of course, as it's an expensive idea. So, what is the basic problem in any algorithm, anything in any program?
I mean, the classic answer is the halting problem. I'm not sure that's what you're getting at, though.
It can be related, but okay. The idea is that instead of adding more and more instructions and making the chips more complicated, I mean, if you look at the modern chip, it includes hundreds, if not thousands, of small and isolated and specialized units that do a particular job, right?
Mm-hmm.
But what is the fundamental problem of every algorithm and every program that you are running? You want to make it faster.
Mm-hmm.
I can add 1,000 instructions in the CPU. The main problem is memory access. That's the main problem. That's what the companies realized when Apple released their first CPU, the first Apple Silicon, the M1. Why was it so difficult, so different from the other CPUs? Because they put the memory chips right next to the CPU. No memory controller or expensive routing, or it was literally next to the CPU. And they managed to increase, especially in the ultras, they managed to increase the bandwidth to, at that time, 5 years ago, to almost 1 terabyte per second. It was 800 gigabytes. So, 800 gigabytes per second.
Yeah.
That was crazy at the time. At a consumer chip. It was not a data center chip. It was a consumer chip. Why? How did they solve this? Because they put the memory close. So the trend right now, you see systems like the NVIDIA Grace. It offers like, I think it's about 5 terabytes per second. Again, they solve the problem by moving the chips right next to the CPU and GPU by using HBM memory, specialized memory, etc.
I was going to say we see this with HBM and HBM2.
Exactly.
HBM3 is coming.
Now, what if you take this one step further? On the wafer.
Bake the memory right into the CPU. Yeah.
Yeah, exactly. So imagine if you take, this is what I see next. I mean, if I can have, right now the average latency from the CPU to memory is about 20 cycles, sometimes more. What if you take that, but if the access time to L1 cache is 1 cycle? What if you can manage to take, let's say, create a level 3 cache? Or no, ignore the level. You don't need caches after that.
Right.
If you have memory, so a cache-less architecture does not need cache. You have memory on the wafer. Imagine that you have the scale. So there has been.
Or you could say that another way. It's all cache. There is no more memory. It's just all cache.
Yeah, exactly. That's why I would like to work on that kind of project, to be honest.
Yeah.
And I started working on the architectural part. Of course, I cannot produce my own CPU, That's going to be. But you know Cerebrus? Have you seen Cerebrus, the AI company?
I think so.
Check it out. So what they did in a novel design, they sort of did that, but only specialized for AI. They especially the whole wafer is a chip.
Yeah.
They don't split it in multiple products, let's say. So they don't produce a wafer. It is the whole chip.
It's sort of the next step in the SoC,
Yes.
the SoCification of computers.
Yes. Yeah. So you will have a chip. That's the trend that I'm seeing, and what I think is going to happen afterwards. You will have a huge chip, a huge CPU or GPU or whatever. Doesn't matter after that.
Yeah.
You can have extremely large amounts of memory on the die, on the wafer. Some logic. It doesn't really matter if you have 1 or 2 or 1,000 cores. It doesn't matter because the memory is available. You can have a single core with 1,000 others, or 1,000 cores with one other each. It doesn't matter because the memory access is going to be instant. So that's what I think is going to happen. And okay, who's going to do it first? I don't know. Maybe Nvidia, maybe ARM, maybe Intel if they get their things together. I don't know.
Yeah.
Maybe IBM on a Power 12. But then again, IBM is not going to be interested in in selling them to consumers.
Right.
And this is going to mean that you're not going to be able to have, let's say, a laptop. You cannot have a laptop that's a wafer. So this is going for data
at least
center.
not anytime soon.
Not soon, yes.
Yeah. Yeah, it's interesting as you kind of look back through history, the history of computing. We started with, room-sized computers where everything was broken out, and then it kind of moved into microcomputers where more things were brought in. Then mini computers, more things were brought in. You finally get to the SoC. We're kind of in that SoC era right now.
Yeah.
Where a lot of it is on the same wafer, but you've got your memory and some other things off of it.
Yeah, that's true. I mean, I was seeing a diagram. I think it was from a Samsung CPU or an Apple CPU. And the ARM core itself was only a very small part of the CPU, of the die. Everything else was just a decoder and a controller for that peripheral, and that was the TPM chip, and that it was the whatever. I mean, there was a dozen different modules on the same die that were occupying the majority of the actual silicon, and the ARM core itself was only a small fraction.
Yeah. Yeah, interesting times. All right, we have covered the hour, a little over actually. So I want to ask a few final questions for you. One is there anything we didn't talk about that we should have?
Know.
And that was a tough one because you got to think about everything we talked about.
I think we covered everything.
All right.
Well, I have to mention the obvious. I mean, if anyone is having the is interested in making their software faster, okay, yeah, feel free to contact us. I mean, VectorCamp.gr is the website, and feel free to send us an email. We're a small team, but we are very agile, very, very focused, and very good at what we do.
Yeah, yep, excellent.
So,
and then you personally, I've got to ask, what's your favorite text editor and scripting language? What do you spend all day in?
text editor. Okay. So I'm a Vim guy.
Okay.
I also use VS Code, but I guess I've used everything in the past, from the huge IDEs for Java like Eclipse and JetBeans. I don't like this kind of stuff, so please no Java.
Yeah.
And language is fine. I don't like the ecosystem.
Ah, interesting.
Yeah, I mean it's huge. And the editor, and what else?
Your favorite scripting language?
Scripting language. Well, for a single shell stuff, I use Bash. But for something more complicated, I use Python.
That's a pretty standard answer. I find that a lot.
Yeah.
A lot of folks are sort of in that dichotomy.
Though to be honest, I started playing with Zig recently. I'm very, very interested in that language. I would say it doesn't have proper CMD support yet.
Ah,
It has some vector data types, but no CMD intrinsics, which is a major drawback for me because I cannot use it. To get the max performance you want, you have to either use assembly or intrinsics. I mean
yeah.
the high level abstractions, they work, but only up to a point.
Right.
They don't work if you want max performance.
Makes sense.
Yeah.
All right, Konstantinos, thank you so much for your time
I
today.
have to thank you.
It has been a blast. Appreciate you being here.
Thank you. It's really thank you for having me, and it's a nice, I don't know, it's a light in the ocean of YouTube to talk about free open source software, and
Yeah,
with someone that really appreciates.
Yep, that's one of the things I really enjoy about the show
Yeah.
too. Like I said in the
Thank
pre-show,
you.
we just get to sit
And
down.
I have to thank Robert for this also.
Yes.
I
Yep.
have to mention that.
Yep, absolutely. Robert from over at Devico hooked us up and put us
Yeah.
together. So, all right,
Yeah.
appreciate it so
Feedback.
much. Yeah.
Thank you.
All right. I do want to let folks know if they want more of me, there is, of course, the Untitled Linux show over at Twit. And then also keep an eye on Hackaday. You can see some of my other things, what I get up to there. And other than that, just want to say thanks so much for everybody being here. Next week, we have KS Bashkar of YadaDB scheduled. And then the week after that, we're talking with Jonathan Thomas about OpenShot. So looking forward to both of those. We appreciate everybody that's here, those that watch, those that listen. You get us live or on the download. Thank you so much. And we will be back next week for another FLOSS Weekly. All right. Cool.
Thanks. So I just log out, right?
Yeah, you can take off. I'm going to record a title and tease. Some of that background stuff, and then I'll get to editing on it. This will go live on Hackaday tomorrow. I'll try to remember to shoot you an email when that happens.
Perfect. Thank you.
All right. Thank you so much. Have a good one.
Bye.
Bye. Nope. That button. There we go. All right. We had some fun show titles. Which one? SOCification. I may go with that. That one's fun. It seems like there's a... Okay, I'll do it. I just so happen to have. Some of those are fun. SOCification. I like that one. All right. Hey folks, this week I talk with Konstantinos Margaritis about, well, SIMD instructions and open source architectures. What's going on with x86-64 and ARM and long soon. We talked about a lot of different stuff. He's been a Debian developer for about 25 years, got quite the career, and we cover a lot of it. This is FLOSS Weekly episode 857, recorded Tuesday, December the 2nd. SOCification. Hey folks, this week I talk with Konstantinos Margaritis about, well, open source architectures, long soon, x86-64, and a lot of SIMD. That's single instruction, multiple data. It's a lot of fun and you don't want to miss it, so stay tuned. This is FLOSS Weekly, episode 857, recorded Tuesday, December the 2nd. SOCification. All right, one of those will do. Thank you everybody for being here. We'll see you next time. Bye.